So let me comment that, well, infinite dimensional mathematics is a bit peculiar in some sense. So finite dimensional mathematics, there's sort of just a bevy of examples lying around you, and the first time you encounter an abstraction, it's like, oh, right, those 5 things are all examples, right? So the examples somehow you already know, and the theory organizes them. In the case of infinite dimensions, you're not automatically familiar with anything infinite dimensional. That's not an automatic thing. So it's not like there's examples lying around. So the theory is the easy part. So the theory of Hilbert spaces is totally straightforward. It's very easy. The hard part is constructing a single example, right? That's why if you've done quantum, you've seen maybe what a Hilbert space is, but you've never actually seen, an example of a Hilbert space actually constructed, apart from something like c to the n, right? Okay, so we're doing the hard work now, which is constructing an example of a Hilbert space, the example of relevance, which is L2 spaces. And then we'll do the theory, but that'll be very quick, and we'll get through a lot very rapidly. So we're doing the hard work right now in the theory of Hilbert spaces, even though I won't say that word until we've already succeeded, right? Okay, so let me remind you what's been happening. So, well, we talked about function spaces, and then we know that these are infinite dimensional vector spaces, unless X is a finite set. Central example is space of real valued functions on a circle, and we've discussed how that vector space, well, it's a topological vector space, so I can talk not only about the span of a set of elements, but about the closure of the span. And our discussion in the tutorials last week was the argument that taking the span of this collection of functions on the circle and taking the closure, this span, as we argued, is exactly the things that can be written as polynomials in sine and cosine. So this is the set of trigonometric polynomials, even though they don't look like polynomials, they just look like spans of a set of elements, but they're actually, if you like, to think about them, they're polynomials in cosine and sine. That set does not span this space, but the closure of the span is the whole space. Okay, so that's a really new object in our experience. It's something like a dense basis, right? So it's not that you get everything by taking linear combinations, but you need to take limits of linear combinations. And we don't have a good formalism yet for talking about that kind of situation, but nonetheless, that's clearly important to be able to understand functions on the circle. Okay, so we have to grapple in a serious way with this kind of situation, and I outlined how integrals are the key to doing that. Now, trying then to incorporate integrals into the story with function spaces leads to these normed spaces, but then we encounter at least 2 problems. The first problem is that, well, which one do we choose, right? For every real number p between 1 and infinity, we have this normed space, well, a norm on the same vector space, and if we're trying to understand this story, which one should we pick? It's not a priori clear which one is special. There is a special value of p, which is 2. Well, there's 2 special values. One is 2, as we'll see, for reasons that aren't obvious, but which are very beautiful. So p equals 2 is special. P equals infinity we understood already, right? That was the d-infinity metric, which is the compact open topology. That is of sort of fundamental importance in its own right. So we've already established that p equals infinity is special and why it's useful. P equals 2 stands to be still explained. So that's one question, which p should we choose? The other question is, well, as we saw in this example last lecture, these spaces don't need to be complete. So a normed space which is complete in the induced metric is a Banach space. So that is to say, this pair is, at least for this example, is not a Banach space. So that's 2 problems. Okay, this problem is in some sense the easy one to fix. So we just take the completion. Okay, so that's what we got through most of the way last lecture. So what is the completion? Well, there's various flavors of it. They're all related. So one version of the construction, which is where I started and what I nearly finished last lecture, is a construction which assigns to every metric space a complete metric space just by adding in some sense, formal limits of all Cauchy sequences and then fitting that together correctly. All right. I can also start with any normed space and complete it to get a Banach space. And there's many other kinds of completion in mathematics, but these are the two relevant ones. Now, these are related, right? Because a normed space, if I take the induced metric as a metric space, so going from a normed space, forgetting the norm, but remembering the metric, I could complete it as a metric space, and then I could ask, well, can I then induce a norm on this to construct this error? So that's what we're about right now. Okay, so that's the preface. Now we dive back into the proof of the first row there, which is completing a metric space. But before I get into that, are there any questions about the sort of general picture at this point? Well, given the introduction I just gave to this story, maybe I should mention that. So this symbol here, as you can see it there, stands for completion. So taking this normed space with p equals 2 and completing it is an L2 space. This is a self-dual Banach space. And it's that self-duality which tells you that you're looking at a Hilbert space. And that's for whatever reason nature has chosen to use as the underlying mathematics of our best theory of, say, particle physics, which is a Hilbert space. Okay, so this is a very beautiful fundamental object, and we're about constructing it. Okay, so we got to the end. We only had left to prove that this was complete. All right, so let's do that. Okay, so well, what do we got to do? We've got to take a Cauchy sequence in X hat. And we have to show that it converges. Right, so each Fn is itself a Cauchy sequence, right? Or rather an equivalence class of Cauchy sequences. So Fn, for a fixed n, is a Cauchy sequence in X. So this is a Cauchy sequence of Cauchy sequences. And somehow I've got to construct the limit. Well, there's a few ways of going about that. Now recall that we proved that X, the original space, was dense in X hat, which is to say, so we remember that we identify X with the subset of constant sequences in X hat, or rather their equivalence classes. That's dense. We proved that last time. We also proved that this is a metric space, so I'm going to use both of those facts in this argument. All right, so that's dense. Well, that means that I can approximate for each n this element of X hat arbitrarily closely by a constant sequence. Right? So I'm going to do that. Okay, so I'm going to approximate Fn within a distance of 1 on n by an element of X. All right, so there's the sequence in X hat. It's Cauchy. I'm going to pick whatever, Qn. Some element like that. So I need some notation for this canonical map because otherwise it becomes even more confusing. So let's call it iota. Right? So iota takes an element of X and spits out the constant sequence, or rather its equivalence class, in X hat. All right, so this is my approximating element, Qn. Yeah, Qn is in X. Okay, so claim that the sequence, which is just made up of those Qn's, right? So I'm just approximating every element of the sequence. Now, the approximations are getting better and better as n increases by construction, so it's plausible that that sequence which lies in X, A might be Cauchy. And B, that this Cauchy sequence, which is a point of X hat, might be the limit of the original Cauchy sequence. Okay, so this is a bit weird, right? Because this F is actually all of those dots packaged together into a single element, right? Okay, so that's the claim, is that A, that's Cauchy, and that B, it's the limit of the FNs with respect to D hat. Okay, so that's what we've got to prove. All right, so let's first show that it's Cauchy. Okay. Well, what do we got to use? We just used that this is Cauchy, right? So we're going to make the F n's close to one another. I don't remember whether this is 2 or 3, so I'll reserve the right to change my mind in a moment. Okay, so we're going to choose n so that that gets very small, and we're going to want to make these very small as well, right? So we want to go far enough along in this sequence so that these are very close, and so that the distances between those guys and their sort of models in X are sufficiently small. So these look like 1 over n. We're making n large. So if n is greater than capital N, 1 on n is less than 1 over capital N. All right, so I also want to make n sufficiently large so that those distances get small. So that's going to take the following form. I can see now I'm going to need 3. Okay, all this means is that if little n is greater than or equal to capital N, rearranging that, I'll get 1 on n is less than epsilon on 3. All right? That's fine, because this is just, there's some n that works, but any larger n will still make this true, so just keep increasing it till this is true. Okay? All right, so I'm trying to prove this is Cauchy, right? So let me do it on another board. Okay. So then, for all m and n greater than or equal to this n, I've got the distance between Qn and Qm. So this is in X, but the embedding of X into X hat is distance preserving. We showed that last time, so well, that's obvious from the definitions. So that's the same as this. All right, and now I can use the triangle inequality to wedge in between these two guys some of the capital F's. So that's less than or equal to Fn. So I'm doing the usual trick using the triangle inequality twice. All right, all 3 of those terms are under control. Right? The outside ones because of the choice of the QNs, and the middle one because of the Cauchy sequence that I started with. So this is, well, that's less than 1 on n by the definition of Qn, that was the whole point, plus, well, that's less than epsilon on 3 because m and n are greater than capital N, and that's less than 1 on m. All right, but now I use this parenthetical here. Right, so those are both less than epsilon on 3. Right, Right, so I'm done. So that's a Cauchy sequence in X. All right, so to see that that's a point of X hat, now the claim is that this sequence of points Fn actually converges to F. And it's basically the same argument. All right, so what am I going to do? Well, I want to make this small, right? By making n large. And what I want to do is go back and compare Qn and some term, and F. So I'm going to use d hat Fn Qn plus d hat Qn F. Now, okay, this I know is less than 1 on n. That I can make small. Okay, so what about this? Why can I make that small? So remember what F is. F is this. This is exactly what we did last time, right? When we showed that X was dense, it was precisely by taking a Cauchy sequence and showing that the sequence of constant sequences, which you get by just ripping out each term of that Cauchy sequence and just replicating it infinitely to get a constant sequence, that sequence of constant sequences converges to the original Cauchy sequence. That was the content of the proof that X was dense. So I've seen this before, so I know I can make this small. Right. So that's why I believe it's true. So let's fill in the epsilon businesses. Okay, so to see that this converges to this, so firstly, so we know that the sequence of constant sequences at the QNs converges to F. That's what we did last time. So given an epsilon, find an n such that for all n greater than or equal to n, the d hat distance between those two guys is less than, well, there's two things here, so I'm going to put epsilon on 2. All right, so that takes care of this. And for this is going to be less than 1 on n, so again, I just need to take capital N sufficiently large. So let's take n greater than 2 on epsilon. All right, so then for n greater than or equal to n, this guy here, which is by definition less than 1 on n, is less than, given this and this, epsilon on 2. Okay, so that's it. All right, so we proved that, first of all, we took a Cauchy sequence, we constructed a candidate limit, which was itself a Cauchy sequence, and now we've proved it converges to that limit. So we're done. So we've constructed the completion of any metric space. So what we're going to do now is soup that up, as I sketched here, to involve norms. Is there any question about the argument there? So at first, in some sense, you've swindled yourself into thinking this is totally anodyne in one case, which is the rational numbers to real numbers, right? You use real numbers, you don't feel those are weird, but this looks weird. Well, that's a cognitive dissonance you have, right? So you should either decide the real numbers are really weird and you're distressed by those, or you should accept this. Those are the two ways of resolving that cognitive dissonance. Okay, so that's a construction, but as we've learned in this course, constructions are just one half of the story. You want to know what sort of universal property does that construction have. So I won't quite phrase it formally in this case, but let's discuss now the property which is possessed by the completion, which is that you can lift maps into it in an appropriate sense. Okay. Okay, so here's the property possessed by the completion. Start with a metric space, complete it. So we know, so this map just means the canonical map iota. But, I mean, really it's constant sequences, but that's burdensome to keep in your head. So just think about X literally as sitting inside the completion, and it's sort of like there's some thin layer, like the atmosphere on the Earth around X, which is all the limits of all sequences in X. Okay, if that helps. All right, so that's the completion. And to take a map out of X somewhere, it has to actually be uniformly continuous, not just continuous. But as long as it's uniformly continuous, then there's a lift, which is to say there's a continuous map out of the completion such that, I mean, to say that diagram commutes is just to say that if you restrict capital F to the sort of main part of X hat, which is X, then it agrees on F, and elsewhere it's uniquely determined by its values on X. Okay, that's the unique part. Okay, so we call F a lift. All right. Okay, I claim uniqueness we've already settled. Right, because I proved last lecture that if you have a Hausdorff space, I mean it's a metric space, so it's Hausdorff, and you have two continuous maps into a Hausdorff space which agree on a dense subspace, then they must be equal, right? So if there were two continuous maps, F and F prime, out of X hat with that property, well then they would clearly agree on X, which is dense, so they must be equal. Okay, so uniqueness is covered already. So we just need to prove existence. Okay, so this is a bit of a uncomfortable mismatch of notation, isn't it? Anyway, so now a Cauchy sequence is X. Right, so we need to take a Cauchy sequence in X, that's a point in X hat, and we need to define what F is forced to be. Well, we have no choice. That's part of the argument for uniqueness, right? Because as we've just reminded ourselves, this guy here is the limit in X hat of the constant sequences. So if F were to be continuous, it would have to be the case that it would send that limit to the limit of F acting on the iotas. And by the fact that it's an extension of F, that would have to be the limit of the F xn's. Okay, so if you like, that's a sketch reminder of the uniqueness because we have no choice about what F has to be. It has to be that. So we just define, and that's not an argument that makes sense and exists, but this is the only thing that could possibly work. So we take a Cauchy sequence, we look at its image. The image of a Cauchy sequence under a continuous map is Cauchy, so that's a Cauchy sequence in Y. Y is complete, so it has a limit take that limit, that's unique. So that's a well-defined element of Y, and we define f of the Cauchy sequence to be that element. So that's well-defined. It's not clear that that's a continuous map. It is clear that it agrees with lowercase f on X, but it's not clear it's continuous. Okay, so what do we have to do? We have to check that f is continuous. It clearly makes that commute, and then uniqueness is settled already. Then there's this supplementary assertion that this unique f is actually uniformly continuous. All right, so we need to check that as well. Well, I should tick that. Okay, so that's the checks that remain to be done. I'm actually going to skip these checks because it's all the same stuff we've been doing. So it's basically very similar to this. There's no real content to it, which is to say that, I mean, this would be, I think, a perfectly reasonable exam question to just sit you down and say, prove those 2 points. You should be able to do that. That's routine at this point. Okay, so I'm going to skip it. All right. So that means that we've got this ability to lift maps from a metric space to its completion. So now I want to discuss completion of normed spaces. Maybe it's worth pointing out, pay attention to the hypothesis of uniform continuity. That's actually not just technical, it's actually very meaningful, as we'll see in a minute. There's an example in the notes of why it fails in the case where it's not uniformly continuous. But that's not a small wrinkle. That actually has significant implications. Okay, so let's state the theorem of completion for normed spaces. Okay, so that remains to be completed. Okay, so let V be a normed space. So take the associated metric space. And then complete it. So remember, the associated metric space has the distance between vectors v and w is the norm of their difference. I'm putting a subscript on the norm because I want to write in a minute the norm on v hat. V hat will be the norm completion. All right, so we extract the metric structure, we complete it, that's a metric space. Okay, so at the moment that's just the metric space. I claim that I can put a vector space structure on v hat and a norm in such a way that the norm has as its associated metric this thing. Okay, so the operations on v hat are plus and the action which I defined in the obvious way. So I take two Cauchy sequences in my vector space and I just add them term-wise. It's an easy check to see that that's still a Cauchy sequence and it's well defined on equivalence classes so that this thing is a well-defined operation on v hat, and scalar multiplication by a Cauchy sequence is just term-wise. Right. So that could or could not, that may or may not be an actual structure of a vector space, but at the moment it's sort of plausible those are well-defined maps. Okay, so I claim that makes this into a vector space, and then I claim the norm, which is defined to send so the norm of a Cauchy sequence is just the limit of the norms of all the constituent elements in V. Right, so that's first claim. So that's a normed space. This normed space is a Banach space. That is, it's complete. Okay, so once I've defined a norm, I get an associated metric. I need to check that actually is the metric I started with. And that with respect to that metric, this space is complete. So I have a map from V into this new norm space. Well, as a set, this is just the old construction, right? This is a metric, the underlying set of a metric space. This is the completion, so this is Cauchy sequences. So this is the iota we just discussed in the metric space case. And the canonical map is norm preserving and has dense image. All right, that's a theorem taking up 2 boards. I think that's enough. Then there's the extension statement, which generalizes this, but I'll state that separately, maybe. So this Banach space, V hat, so it's called the norm completion of V. All right, so what is there to check and which parts are obvious, which parts are not? Okay, so as I suggested already, this part is routine. So to check that that actually makes it a vector space, we won't worry about proving that. Okay, that leaves dealing with the norm, but for that we can use this. Okay, so okay, so what did we start with? We started with a normed space. Then we extracted a metric. Okay, so that's a metric space. But the norm, an exercise asks you to check, that that's not only continuous as a function from that metric space to f. Remember, f is either r or c with its usual metric. Not only is that function continuous, but it's uniformly continuous. Okay, all right, so then we can apply this, right? We've got metric space, complete metric space, both r and c are complete. That's a complete metric space. What's the completion? So there is a unique, so there exists a unique, uniformly continuous map, which we'll show in a second is a norm, but for the moment it's just a uniformly continuous map out of the metric space completion with values in f. Okay, which makes that diagram commute. That is, it restricts to the old norm on V. Okay, so we need to show that map, which we've produced, actually is a norm. And then we will have succeeded in producing at least a normed space. And if we can show that the associated metric to that norm is the underlying metric on the completion, well, by definition, that's a complete metric space. So that will show this is a Banach space, right? Because the associated metric is a complete metric space. So then we'll be done with, well, basically the rest is for free. Okay, so that's what we're going to check, that it's a norm. Well, what is the formula for it? That came out here, right? Since it's continuous, it sends limits to limits. So it must be the case that I mean, I knew what the formula had to be, but this way allowed me to just escape having to prove it was, continuous. All right, so this has to be the limit as n goes to infinity of the norms of all the Vn's. Okay, so let's prove this is a norm. So what do we need to show? We need to show so we need to check that. But this guy here, if it's a limit, well, these things here are all non-negative by the fact that V is a normed space. So that is, they lie in the closed set, which is all things greater than or equal to 0 in, well, I'm sorry, maybe this is in the notes as well. I mean, norms land in R, not in F, right? No matter what F is. If F is C, it doesn't matter. The norm is still a real number. Okay, apologize. Okay, so this is a non-negative real number, and therefore the limit is non-negative, right? Because that's a closed set, the non-negative numbers. Okay, so that gives you this. Well, suppose that it was actually 0. That is, that this thing here, this limit was 0. So that's done. Well, what does it mean for a Cauchy sequence to be 0 in V hat? So the 0 vector, by the way, is the constant sequence at 0. To say, what does this equality mean? This is not a strict equality of sequences, right? This is in V hat, so this means the equivalence classes are the same, which just means this is tilde that. Well, the tilde relation says that the limit, right? So to say that those things are related by tilde is precisely to say that the limit as n goes to infinity of d, this is dv, vn 0 is 0. But what is the metric on v? That was obtained from the norm, right? So that is exactly to say that this is 0, but that's the same condition. All right, so by the fact we mod it out by this equivalence relation, this limit is 0 if and only if the equivalence class is 0 itself. Okay. Yeah, so and the other checks are just, again, just passing to limits. So maybe I'll skip this one and do the triangle inequality. Okay, well, by definition of the sum, that's this. And then that's a limit those guys. But again, since V is a normed space, I have for every n this. So moving everything over, that says that's less than or equal to 0. Taking a limit of things which are less than or equal to 0 must give me something less than or equal to 0. All right, so that means the limit of this is less than or equal to the limit of that plus the limit of that, which is what I want. So that's okay, so that was similar to what we did for the okay, so that's the triangle inequality. Okay, so then you check that the associated metric is the metric you started with. Again, that's straightforward. Okay, so that then proves this is a Banach space. The fact that it's norm-preserving is just the same as the fact the inclusion of x into x hat was distance-preserving. Dense image, again, that was by the construction of the metric space completion. Okay, so that's a Banach space. All right. So so remember what all this was for. Right? We have a particular space we want to complete in mind. So take an integral pair. And a P. There's no point doing this for P equals infinity because that's already complete. You won't change the space. Right, then LP, with respect to this integral pair and this choice of scalars, is defined to be the norm completion of the normed space, which is f valued continuous functions on x, together with the P norm. All right, well, by construction, that's a Banach space. And moreover, also by construction, this set sits inside usually you drop the integral, so if you're doing measure theory, you don't really usually put the measure into this notation, but it does depend on that. So you've got a space, an integral, and a field of scalars, but usually you just write x and f. Okay. So that's the completion of this. So this sits as a subspace, as a dense subspace inside of the LP space. Okay, so these are, if you like, fundamental objects of functional analysis, these LP spaces. Now, we saw one example of an element in here which is not in the space of continuous functions, right? Which was the discontinuous function from 0, 1 to r, which had a jump at a half. Doesn't matter which side the jump lives, whatever. Okay, that guy was not continuous, but it was Riemann integrable, and we constructed a Cauchy sequence in this space converging to f in some sense, right? The precise space it's converging in, we didn't make precise, but that f lives in LP of 0, 1. Okay, so often when people discuss these spaces, they present them as certain sets of Riemann integrable functions, modulo and equivalence relation. So we'll get to that, but for the moment, the LP space for us is just some formal gadget obtained by completing the space of continuous functions, and the precise connection to Riemann integrable but not continuous functions remains to be fully explored, but you've seen at least one example. Okay, so that's it. So we've got ourselves Banach spaces. Next lecture we're going to discuss duality. And duality is the deep principle that allows us to pick out p equals 2 as being somehow special.